Hi there. Today we're going to talk about getting started with the Cyclops and Sasquatch Plunger Sensors from Extreme Telematics Corp. So for our agenda, we're going to go over the principle of operation, how to adjust sensitivity, comparison of the various models, how to mount and connect the sensors, and then connecting them to RTUs and PLCs just have a slightly different interface, using Modbus with Sasquatch, and kinetic energy monitoring. And then finally, we'll do a live demo of how to interact with our sensors using our Vision device management software and link device connection. So in terms of the principle of operation, the main system components on the circuit board in all of our sensors starts with a magnetometer or a magnetic field sensor that reads the Earth's magnetic field. We also have a sensitivity dial, which can be set from 0 to 7. These are both connected into a microprocessor that analyzes the data coming from the magnetometer and compares the signal to the switch setting to determine when to close the switch. It's a digital switch, and so what we can do is we can decide to hold it longer or decide when to and when not to close it. So the basics are, we take those magnetometer readings, we filter out any really high frequency noise, as you can see here, and then we try to come up with a long-term average to indicate what no plunger looks like. Then we look for a deviation. So you can see here the red line that was used to get rid of the noise is the baseline. You can see here zoomed out, we see much larger changes when a plunger comes in, and then we can close the switch. We determine that there's been an arrival of the plunger. In terms of the operation internal to the sensor, getting a little bit more detailed, we read samples every 10 milliseconds on the Cyclops and 1 millisecond on the Sasquatch. We need that higher resolution on the velocity sensor because the plunger can be moving very quickly as it goes by the sensor. We do apply this filter, so we take an average of 3 samples to get rid of the high frequency noise. And then every second, we're taking these filtered samples and we're coming up with the baseline. Then at the same time, these filtered samples are also compared to the baseline. So once we have a baseline established, we're using that on every single filtered sample to determine if we've exceeded the threshold. And this threshold is set by the switch setting. So the different sensitivity levels give us a different amount of signal change that we have to see in order to say that the plunger has arrived. So once we've exceeded that threshold and we've determined an arrival, this is how the Cyclops works. We immediately close the switch and we reset the output hold timer. So the hold time by default is 5 seconds. We do have other versions that can hold the output switch for 30, 60, or 90 seconds. So you have to download that special firmware using Vision. But every time a plunger arrival is signaled, we reset that timer. So it isn't necessarily just 5 seconds. If we keep getting arrivals, it will hold it for maybe 6, 7, 10, 20 seconds. As long as the plunger keeps moving, we keep resetting this output hold timer. Sasquatch by default is 1 second, but it can be configurable using the Modbus registers. So if you want it to be 5 seconds or 30 or 60, it's a programmable option in the same firmware. Once the timer does expire, we release the switch. Now, things are a little bit different for the Sasquatch. There's a couple other states that are injected in here. Before we actually close the switch, we calculate the velocity. And the reason we do this is when we go and close the switch, which goes to your RTU or PLC or your plunger controller, we want to make sure that the velocity is in the Modbus register and ready. So we first calculate the velocity based on the data we've been gathering, then we'll close the switch. The other bit of a difference here is once we actually close this switch and indicate there's an arrival, yes, we do have the same output hold timer and we release it after the timer's expired. We also have a reinitialized timer. So we wait for the plunger to actually depart and then we have a reinitialization time. Because there is a log associated with the Sasquatch and we don't want to calculate the velocity on every single arrival because it could be bouncing around. We really want to make sure that we get that first arrival and then don't just clutter up the log. There's this reinitialize timer. So we wait at least a few seconds to make sure that it's gone from the lubricator and we're ready to accept the next arrival. And so in this case, once that happens, we go back to the start time and then start getting readings again. So in terms of adjusting sensitivity, there is a sensitivity dial. Its default is 4, that's the middle of the road in terms of sensitivity, which sets the threshold that's required to trip. And this is on all of our sensors, and it's really to signal the arrival. So it's less to do with, you know, different types of plungers and things like that. It's more about, you know, the amount of ferrous material that's going to take to trigger the arrival, so that we don't trigger on background noise or other noise that other. So you can see here, this is where it's located on the Cyclops, and that's on the Sasquatch. Sasquatch doesn't have anything to do with the velocity, but just when we start calculating velocity in a plunger arrival. So 1 is the minimum sensitivity, or it's the biggest threshold that's required to trigger it, and 7 is the max sensitivity, or the smallest threshold. And we'll show you a demo later on what that looks like. 0 is a special mode called program mode. You can see that in all these cases here. This allows us to interact with these sensors using vision. And so from a sensitivity perspective, we can actually increase the sensitivity beyond what's available on the sensitivity dial. And we do have a support article on how to do that. By default, though, we don't use the maximum sensitivity that's available, because very, very small changes could trigger the sensor. And so we kind of have reserved this as a special feature. Here's an example of a real-time capture. So not only can you use vision to change the sensitivity, you can use it to upgrade the firmware, and you can use it to get real-time data from all of our sensors. So this is an example of a Cyclops, and later on we'll show you what a Sasquatch one looks like. It's very similar, but the blue line here is the filtered samples that we're getting in real time. The green is the baseline, and so we're comparing the blue line to the green line to determine if an arrival has occurred. You can see here we have the switch setting. This one's on the default of switch position 4. What that does is that sets this threshold both above and below the baseline. So it doesn't really matter in the polarity of the signal. If it goes up or down and goes outside these red dots, like you see here, we close the switch. And so in vision, you can see the switch closed here, but in normal operation, we would close the output switch, denoted by the SIG set, the SIG pin. And I'll show you that in the wiring. Also, one other special feature built into Vision is if you're using this when you're commissioning, this will show you in real time as the signal changes what switch setting it would have triggered on. So even if you're on, 2 or 3, it'll show you that you would have been able to trigger on setting 7, for example, when a plunger arrival comes in. So you can use that in real time to help decide which setting to put your sensitivity dial on. So in terms of different models, so we've got 2 different models of Cyclops. So these are the same product, but they're certified differently. This one is obviously explosion proof or flame proof. That's the Cyclops EXP. The Cyclops IS is intrinsically safe. So both of them can be put into Div 1. The explosion proof can only go down into Zone 1, whereas the IS can go into Zone 0. Now, they both work the same way. You can use a wide range of operating voltages up to 24 volts. It uses less than a milliamp of current consumption, and it will just detect the plunger arrival. So we sample at about 10 milliseconds frequency, and then the dry contact, which is normally open, gets closed on arrival. There is this one-wire RS-485 debug interface, and that's how we interact with Vision. So this isn't used from an operational perspective. It just allows us to configure the sensor or to monitor the sensor or upgrade its firmware. Now you'll notice here the Sasquatch uses about 10 times the amount of current, and that's because we sample at 10 times the frequency. Because we need to get higher resolution data when a plunger is moving by the sensor, we're actually looking at how fast the plunger moves from one end of this sensor to the other. We have to sample at a much higher frequency. So we're sampling at 1 millisecond on 2 sensors. It does have an operational interface. It's got a 2-wire RS-485 interface that acts primarily as a Modbus slave, but once again, it can also mimic this debug interface for use with Vision. So That really depends on what you're looking for. Are you looking for just a plunger arrival, or are you looking for a plunger arrival and surface velocity? Then you would use the Sasquatch. All right, so when it comes to mounting, it's a little bit different between the Cyclops and the Sasquatch. So we'll just go over them on two separate slides here. But you use the provided band clamp to strap the sensor to the lubricator. So we provide you a quick release band clamp that can be opened up all the way. You strap it through the built-in legs or around the cable port on the EXP and tighten it against the lubricator. Do make sure that it's tight though and doesn't wiggle, because the sensor's visibility of the Earth's magnetic field will change if the sensor moves. So you want to make sure it's really secure. In general, the Cyclops looks at the movement of ferrous material. A piece of metal that goes by the sensor actually bends or pushes and pulls the magnetic field of the Earth, and it's that deflection that we're looking for to determine an arrival. So if you're using a ferrous plunger, you can just put it at the resting point of the plunger. As long as the plunger gets close to it, you'll actually see that bending of the Earth's magnetic field. And because the Cyclops is one of the most sensitive sensors out there, you can actually put it on the casing or on the master valve. You can detect the plunger multiple feet away. So you've got a lot of flexibility in where to put the Cyclops. It doesn't have to be at the bottom of the lubricator. It doesn't have to be in one specific spot. It'll work pretty much anywhere when you're working with a ferrous plunger. Now, if you're using a non-ferrous plunger, what you want to do is mount it near the anvil or spring up here, because that will be a ferrous piece of metal, and the plunger itself will be invisible. So if you're using aluminum or titanium or stainless steel, you actually won't pick up the plunger. You'll pick up movement of the well components. The only time when that isn't the case is if the manufacturer of the plunger has put in magnets or other ferrous materials for the Cyclops to be able to trigger on. Now, you can also mount it near the trigger rod when you're using a two-piece plunger. So down near the bulb of the bottom of the trigger rod. The problem is that trigger rod can shift around. Sometimes the plunger might come on very cleanly and not move the trigger rod enough. And so this can be less reliable. So even in a two-piece plunger example, we recommend you put it on the striker rod up here, the anvil, to make sure that you get a large signal that can trigger the Cyclops. Now with the Sasquatch, it's the same kind of mounting. We actually provide two band clamps. It has two sets of legs, securely to the lubricator again. And the Sasquatch only works with ferrous plungers. Because we require multiple data points, we need to see the plunger travel by the Sasquatch. So we need to have multiple waveforms so that we can correlate them. And so the plunger must travel all the way by the sensor. So if you can mount it as low as possible, that's going to make sure that we get two complete waveforms, one for each of the sensors in the Sasquatch. And it'll also avoid the bounce back of the plunger, which can skew results. Because if we see the plunger bounce off the anvil and come back down, it could look like it's extending the waveform. So as low as possible, sometimes even taking it and putting on the casing is a better idea. All right, so here's a capture of the Sasquatch. So it looks very much like the Cyclops. You have your baseline. There's two different baselines here. There's two different sets of real samples. There's obviously two sensors on the Sasquatch, as well as the threshold is set here based on the switch setting. We've got this up to sensitivity dial 7, so that's a really small change we're looking at. And you can see we deviate from the baseline, and we're pushing and pulling that magnetic signal, which gets triggered as an arrival. So if we zoom in, it's looking for points that it can correlate. You can see there's definitely a time shift here, but the waveforms look pretty much identical. This plunger traveled by relatively at a consistent speed, so the waveforms look the same size. But because it might travel by and accelerate or decelerate, we look for things that are common or constant, which is the minimum, the maximum, when we cross the baseline. And we try to come up with the average of these times. So, in this case, we've come up with what we think the average distance between the waveforms are, and then this time can be used in the velocity calculation. So it's very simple. Velocity is distance divided by time. The distance is set by the spacing on the circuit board between the sensors, and then the only variable really here is the time. So the less time between these, the faster the plunger is moving. As for physically wiring the Cyclops or Sasquatch, they both have the same power and signal connector. So you can see here we've got COM, SIG, power. So COM is common or ground. That's going to be attached to the ground of your controller. SIG is a dry contact output, and we'll talk about that more on the next slide. But basically, SIG is shorted to ground or common, and so we complete the circuit when the plunger arrives. So normally it's open, and then we close it on arrival. And then, of course, we got to give it supply voltage. Because it is a microprocessor-based system, it does have to have power provided. There is no internal battery, and there's no other way to deliver power other than through this pin. So it is a 3-wire connector, both with the Sasquatch and the Cyclops. Now, on the Sasquatch, there's an additional connector. This is for that Modbus RS485 slave connection. And so, once again, there's a COM in there, and then there's an AB, which is a 2-wire RS485. With the Cyclops, the SIG pin is used for that 1-wire RS485 interface. So we do have a special circuit that's implemented in our link device connection that allows you to connect to the Cyclops without having to use a regular RS485. Now, if you're going to use an RTU or a PLC, there's many cases where they don't have a dry contact input, like what we have in our Alien 2 plunger controller or all other plunger controllers. They have a voltage input. So the way that a dry contact input works, and this might exist on some of your RTUs and PLCs, so you want to make sure that you check that first. There's an internal pull-up resistor in the controller side. So what happens is, when the Cyclops, which is a normally open, or Sasquatch, or any plunger arrival sensor, there'll be a normally open switch. And so when it's open, there's no circuit, you don't have a voltage coming back in SIG. So this pull up in here to power allows the input on the microprocessor to see a positive voltage or a high voltage when there's no arrival. And then, as we mentioned before, when the arrival is signaled, we close this switch and signal is connected to common or ground, then that'll pull it low. So it'll go from being high on a non-arrival to low during an arrival. On a voltage input, though, it's expecting a voltage all the time. And so it needs to see a high or a low voltage coming into the RTU or the PLC. And like I said, with Cyclops or Sasquatch, the switch is open when there's no plunger present or no plungers arrived. And so you get an indeterministic value. So that undefined value can confuse these PLCs and RTUs because they don't know if it's high or low, and it's essentially floating. And so you can get premature arrivals when there's no arrival actually present. So instead, what we do is we do the same thing, this pull-up resistor to power, but we have to do it externally. So use a 100K pull-up to power between SIG and power. And then if the Cyclops or Sasquatch is open, once again, power is going to get fed back into SIG. And then when we short this to common or ground, then it's going to go low to a low voltage. So there is a support article on this on our website. There's also in the Cyclops and Sasquatch manuals, it explains how to do this connection. All right, so when we're using the Sasquatch, we do have the Modbus port. So this is used for a number of different things, such as configuration settings, retrieving the velocity value. So it is a standard RS485 connection. The COM port settings are 9600 baud, 8 data bits, no parity 1 stop bit. This can be changed in the Modbus configuration, but this is the default you'll have to use when you first connect with it. And you can use Vision to configure it, or you can use your own Modbus tool. Then as well, what's important is you got to set up the sensitivity dial. If you're on 0, this COM port acts as a programming port with Vision. So you can, change its mode, you can send it commands, update its firmware, those kinds of things. When you're in an operational position, such as 1 to 7 on the sensitivity dial, it acts as a regular Modbus slave. So you can use it with any Modbus master program to access the configuration registers, the logs. So some of the key registers, and this is all in the Sasquatch user's manual, so I ask you to refer to that if you're going to set up an integration with the Sasquatch. You want to make sure that you set the date and time, as this is used for the log entries. There's a couple different ways that the date format is set. but there's 6 registers here, the holding register 2 through holding register 7. And then the arrival log is the most important. If you read the head of the log, it is a FIFO, or first in, first out. So the latest arrival is always at the top. So if you don't care about all the log entries, you can just read the top arrival. There is 4 pieces of information. You get the arrival time and date, which is coming from this date and time register here. And then it obviously runs. The velocity of that arrival, a confidence code, and then we also give you the kinetic energy if you've set the plunger mass. Now you'll notice these registers are all spaced out because what we've done is we have all of the log entries, like there's a number of arrival times, so they're all stacked here and then spaced out. So then all the velocities, all the confidence codes, and all the kinetic energies. For the confidence code, this is once again in the manual, but the different numbers obviously mean something different. Numbers 1 to 8 is telling us how many points we're correlating between the waveforms that are coming off of the magnetometers. So there's up to 8 data points that we can correlate. And then there's special codes that are in the 20s. So 20, 21, 22, 23 is velocity under range, over range. We're unable to synchronize the waveforms or capture the waveforms, or we start calculating and find out there's not actually an arrival. Now, it's not all just about velocity. Velocity is the value that we're reading. So you can use the Sasquatch to just read this velocity. You can bring that into your SCADA system or make decisions on it with your controller. But you can actually get a bit more intelligent. What really we'd like to see is people using kinetic energy. We have implemented some features in the Sasquatch to do kinetic energy, and this is more as a demonstration, or if you don't have it in your SCADA system yet and you want to start to calculate kinetic energy, the impact of the plunger at surface, because that impact is going to vary with the mass of the plunger. So you do have to set the plunger mass in the sensor if you want us to calculate kinetic energy. But when you're setting up your actual alarms and shut-ins on your plunger well, velocity on its own really is meaningless, because it's really about the impact that the surface equipment can take. So if you do have that plunger mass in, kinetic energy is equal to 1/2 mass times velocity squared. So the velocity is obviously the most important factor, but you're going to get a harder impact if that's a 5-pound or a 10-pound plunger. And so we can calculate kinetic energy in imperial or metric. It's up to you. Those units can also be set in the sensor so that you get back the calculated value and the units that you want. And then once we have the kinetic energy, whether this is done in your SCADA system or whether it's done in the sensor itself, we can start to alarm in real time, because now we have every arrival's kinetic energy. Instead of just looking at the number of arrivals or the velocity of arrivals, we can get the kinetic energy each time so that we can identify single dangerous hits, consecutive hard hits, or we can add up cumulative long-term kinetic energy to try and predict the spring wear or the wear on the plunger. And so you'll see in this case here, if you're using average velocity, we can see that this plunger took a while to come up and it ended up venting, but it's hard to determine that arrival was a problem compared to all the arrivals around it. It looks like it was a slower arrival, but now we're looking at surface velocity, and once we turn that into kinetic energy as well, you can see that impact was dramatically harder than the average arrival. And remember, this velocity value is squared. So it's not just 4 or 5 times, right? It's 5 squared. So it's like 25 times harder. All right, so in order to get more details on how to work with our sensors, we do have a support center, and this link is clickable if you want to visit there. But basically, you can ask a question like, how do I upgrade the firmware, or how do I see what Cyclops or Sasquatch sees? Access to training programs such as this one. There's product resources, documentation, tools, accessories, replacement parts. This is your one-stop resource. So if you click on products, you can go to Cyclops or Sasquatch and get everything you need, including a free download of Vision. submitting RMAs, submitting a support ticket, we really encourage you to use our self-service support center first and contact us if you need additional assistance. Now, I am going to show you a live demo of the Vision software. So this is the Vision software. Once you've installed it, it comes up to this Home tab. If you go to Setup, you can see we can pick the device we want to talk to. I've got a Sasquatch here, and I'm going to connect to it. We pick the USB serial port, which is the link device connection I have plugged into my laptop here. And I'm going to go and connect. And we can see this sensor is already in the full debug. If we put it in switch position 0 and set it between normal and full debug, we can change the mode. So you can see normal is the normal operation mode. When you're done kind of working with a sensor, you always want to go back to normal. We can do a self-test. We can do full debug, which shows us the baseline and switch setting, all the detail I showed you in some of those other screen captures. Or if you want to see the raw data with no filtering, you can see these raw samples. And then you can click set or get mode. But we're already in the full debug mode. We're going to go over to capture here, and we're going to start it. And it's just, once again, it wants you to be in an operational mode, so between 1 and 7. And when we start this, you can see with the Sasquatch, there is 2 waveforms happening here. We have the baseline and the samples are relatively the same because there is nothing affecting the Earth's magnetic field. You can see that the threshold, we're on sensitivity dial setting, so it's a really small change from those baselines. And it's sitting here looking for an arrival of the plunger. And so I'm going to actually take a screwdriver and we're going to run it underneath here. And you can see that when I do that, and I'm just going to stop it here so that we can see what's happening. It will start automatically looking again once that reinitialize timer goes. But if we stop here and actually look at what's happened, you can see we see the same waveform here. We see it dip and then go up, and you can see that there's that time difference. And then eventually it goes back to monitoring again. But you can see is if you're messing with the sensitivity dial switch and stuff before you do your capture, it might not start recording data right away because it's paused while it collects data and analyzes the velocity. It will start to spit out data pretty quickly. So that's just a quick example. Some things that you can see here, the switch goes back to open. It was closed when it triggered. Once again, the sensitivity dial setting. We have a velocity number. I ran it below the range of this sensor, but if you move a screwdriver or a plunger by it more quickly, you'll see the different velocities come by here. We've also got some stats of the types of samples it's reading and the mins and the maxes and the baseline. So you can determine what you see here is, sensor A and sensor B, baseline threshold. So you can start and stop it. You can also log this to a file. So if you want to record this data for later, you can. But like I said, I want to encourage you to come in here and see how the sensor is working. This is a great tool, especially for commissioning the Sasquatch. When you want to make sure that you're getting, clean waveforms, making sure that the plunger's arriving, see some samples of velocities you're getting. And then once this is set up, then, flipping over the connections to work with your RTU or your PLC or your plunger controller. So that's about all I have for today. ETC, we are experts in low power, wide temperature range, hazardous locations approved electronics. We've been in business since 2001, almost 20 years. We have around 70,000 to 75,000 devices out there right now, 12,000 controllers, 60,000 sensors. We really do want to democratize industrial automation, have some strong core values. We'd love to work with you on the devices we already have or future devices you might need in order to make your wells optimize efficiently. And if you want to learn more about us, please go to our website at etcorp.ca. If you click on the About Us link, it'll give you a bit about our background. You can see our management team, more information about all our products. And of course, reach out if you have any questions about the company or about our products. We'd be happy to help.